Okay. Shall we start, Nagaraj Kumar?
Yes, yes.
Okay. Good afternoon to everyone. I welcome all of you to the 29th lecture in the lecture series in Nonlinear Dynamics conducted by the Department of Nonlinear Dynamics, Bharathidasan University, with the support from RUSA 2.0. It is my pleasure to introduce you today's speaker, Professor C. Nagaraja Kumar from Punjab University, Chandigarh. Professor C. Nagaraja Kumar is a well-known person to us. He has been associated with our department for more than 2 decades. I wish to read out his academic achievements in a very brief manner. Professor Kumar completed his MSc in the University of Hyderabad and did his PhD at Institute of Physics, Bhubaneswar, one of the premier institutes in physics in India. Thereafter, he carried out his postdoctoral work at different places about 6 years and joined as a permanent faculty in the Department of Physics, Punjab University, Chandigarh, in the year 1999, and still serving at the same place as professor. I met Professor Kumar at several occasions. The last one was at his home place, Punjab University. I was attending a meeting in Amritsar, and on the way back to Delhi, I made a visit to his department by invitation. It was a nice experience to deliver a lecture there. Professor Kumar's main interests are constructing various types of solutions for the nonlinear systems which arise in nonlinear optics. He has trained a large number of students in research. When I invited him to deliver a lecture in this forum, he immediately accepted. Thank you for the same. With this short introduction, now I hand over the session to Professor Kumar. Over to you, Professor Kumar.
Thank you very much, Professor Shintalvelan. And I thank Professor M. Lakshmanan also for being the part of the audience. Really, it's an honor for me. Okay, so let me start without much ado. So this, we have heard finite number of very good talks from experts. So here I will be explaining a reasonably interesting way of how to control the amplitude and the width and the intensity of a nonlinear wave in a given system. Okay. So controlling nonlinear waves, the Riccati way, that's the title which I have given it for this talk. So I shall try to explain very briefly to this audience, which is already very familiar with solitary waves and solitons. And then how does the electromagnetic wave propagate in an optic medium as an example. Then we'll make a good digression about how the Riccati parameters enter into this analysis. This Riccati parameter enters in a very interesting way in quantum mechanics. For the last 20 years, this idea is with us, and we could do some few things. And I'll try to explain how we could generalize the kink-bearing Hamiltonians, and how this is also useful in atomic molecular physics in calculating Frank-Condon factors, and also a very good application of the study of dynamics of charged particle in a non-uniform magnetic field. So after that digression, we'll come back and how to control the excitations, various nonlinear excitations that are possible in the nonlinear medium. So this is the title of this is the plan of the talk. So the first 2 parts will be roughly around 20 minutes, and the digression will take around 20-25 minutes. We'll come back and conclude how the Riccati parameter controls the excitations. Let's start. We are all familiar with waves in our day-to-day life. The wave is the result of some physical event that sends disturbance through the medium, a pebble thrown in the lake, or the transmission towers transmitting the signal from the source to the destination, or any vibration which is produced by various stringed and precursor musical instruments. So these waves will form, they travel for some distance, they disperse, and finally they die down as a function of x and t. So what's the standard familiar one-dimensional wave equation we will write? It's d square u by dt square minus c square u square to x square equal to 0. So you got any function which is the left moving x minus ct, right moving x plus ct, both are the, so linear combination is also a solution. The dispersion relation is omega equal to ck, and we know that the phase velocity and the group velocity will be the same. So this plane wave will travel for long distances in time. Nothing great is there in a freely moving wave, so we want some interaction to take place. So either dissipative wave. So what is the dissipative wave? If you have a XXX term, the dispersion will no more be linear. It's a nonlinear dispersion equation. So the phase velocity and the group velocity are no more the same, which means the different phases of the waves will collide and the waves will disperse. So XXX term is the reason why the wave disperses. We can also have a case of UXX, second derivative of u. Here the dispersion relation will turn out to be imaginary. So if you can work out u of xt, as the time progresses, the waves dies down, e to the power minus k square t is the signature for the dissipation of amplitude as a function of time. So we have seen dissipation, we have seen dispersion, and if you have a nonlinearity in the picture, if only nonlinearity is there in the picture, the wave will break up or the function will have multivalueness. That would be the mathematical definition of nonlinearity. Sorry. In case either the dispersion and nonlinearity or the dissipation and the nonlinearity, if both are present in the system, and if it so happens that they can actually neutralize the effect, the dispersiveness as well as the breaking of the wave, then a stable localized solutions is possible. So such a thing indeed does happen, and such a wave is known as a solitary wave. A non-singular localized wave propagates without change of its properties, shape, velocity, etc. One of the most familiar solitary waves we have seen is a bell shape, secant x minus ct. This has an interesting history. John Scott Russell is the person who made the observation of a solitary wave for the first time. It's the part of the standard folklore, so most of the audience might have already seen this view graph many number of times. So I won't be reading it out in full glory. So Scott Russell made this original observation. He was a architect, naval architect, and basically a canal supervisor in some sense, I guess. So not only he observed it in the nature, he came back and performed a series of experiments and found out that the taller wave travels faster. C is the velocity, h is the height of the wave. So the taller the wave, the faster it travels. So this solitary wave has been reported in the literature, and some on the occasion of a international conference, and I think around 100 years of the KdV equation, it has been recreated in a canal in Glasgow. So these phenomena attracted a lot of scientists. Now it's well known, KdV, two Dutch scientists, Korteweg and de Vries, they presented their famous equation for the evolution of long waves in a shallow one-dimensional channel. In a completely different context, Los Alamos National Lab, Zubovsky and Krushal, they are working out how does the energy distribution takes place in a nonlinear lattice. does the energy equipartition theorem holds good or not? And while doing that analysis, they realized that there is a super cycle. After some time, the energy comes back to the original mode, and a continuum version of that anharmonic lattice led them to a KdV equation. So Zubowski and Krushal, they solved this equation numerically as a model for nonlinear lattice, found that the solitary waves interacted elastically. That would be a normal nomenclature to give ON for any particle type of objects. We'll call it solitons. So now, what is the difference between a soliton and a solitary wave? A solitary wave travels without change in shape or velocity, but even after collision, if it retains its shape and velocity, then that's called a soliton. So a soliton is a self-reinforcing solitary wave of a nonlinear evolution equation, which represents wave of permanent form, localized, or it decays to a constant value. Okay, so that need not be that it should go to 0 only, it can go to a constant value. Again, the most important property is it's stable against the mutual collisions with other solitons. So here is a pictorial description. So a taller wave and a shorter wave are made to interact. After some time, some composite body is formed. Again, next course of time, the faster one travels, the taller one travels fast, so it overtakes the short one and retains the shape and the velocity. So the celebrated examples of nonlinear equations are KdV equation, nonlinear Schrodinger equation, and a Fine-Gordon model. These are only prototype examples of integrable models. By integrability, that's a vast subject on its own. One can show that it has infinite conserved quantities. It has n soliton solutions, the existence of lag space. You can prove the system to be integrable using either Hirota bilinear method, inverse scattering method, existence of lag space, etc. So there's a beautiful book, Professor Lakshmanan and S. Rajashekar, Nonlinear Dynamics. The integrability chapter contains very interesting, good reviews. What are all the possible applications of such a soliton excitation? If you put a bit of information on it, it carries for longer distances without any loss of shape or velocity. That's absolutely, for an optical communication, this would be very useful technique. The solitary waves are also studied in the context of fluid dynamics and plasma studies. And very interestingly, even for Davidoff solitons, how the energy transfer takes place in a DNA, you can model it after a nonlinear evolution equation, which is known to admit solitary wave solutions. So not just in hydrodynamics and optics, there are very many fields where these soliton excitations have been found useful. This is a very preliminary derivation of a nonlinear Schrodinger equation, hand waving way, that normally at up to the MSc level, we consider the polarized chi times E. Polarization is vector is chi times electric field, chi is the linear susceptibility. So the nonlinearity enters into the picture in the form of a chi cube. So third order susceptibility is frequency dependent on energy dependent or intensity dependent. So that will give rise to a refractive index is no more a constant. It depends on mod E square. So the P, which as long as it's proportional only to E, that is a linear differential equation. Whereas the moment the higher order effects will come into play, that would be a nonlinear differential equation, and a small amount of mathematics will lead you to very well-known nonlinear Schrodinger equation, I d psi by d psi plus half of psi tau tau. There is nothing Schrodinger about it. It's just like mod psi square, if you consider it like a potential that has a structure of a Schrodinger equation, the potential is replacing the intensity part. So this is the nonlinearity, that is the dispersion term, second and third term. Those two balance each other and give rise to solitary excitations. So this gamma is an interesting quantity. When it is +1, it admits bright solitons. When it is -1, it admits dark solitons of tan hyperbolic form. The bright, it is called the following way. If you plot the intensity, the secant square is the intensity. So over a background of 0, the maximum is 1. So that is the bright soliton. The dark soliton is tan hyperbolic x. So intensity of that is tan square. That is 1 minus secant square. So in the background of 1, there will be a dip, and the progression of this soliton is as a dark bob. So that's how this is called, dark soliton. Along with these two famous well-known solutions, Zakharov and in a different context, Peregrine and all, they also worked out what are the rational solutions of this equation. So these solutions are of the form, as mentioned here, G plus IH divided by D with a minus sign, 1 minus. A first order soliton with G is 1, H is 2IX, and D is 1 plus 4x squared. So rational solutions are also possible. So these rational solutions are really termed out as a rogue waves. These rogue waves are one of the fascinating destructive phenomena in the nature. They have not been fully explained so far. They go by the name of freak waves, killer waves, monster waves. The working definition of this being that the amplitude is significantly larger and roughly 3 times more than the solitary wave. A secant square solitary wave has an amplitude 1. This will have order of 3 to 5. So these rogue waves have a natural history that they have observed in ocean. Some parts of the ocean may have a specific bottom configurations that would make the proper initial condition, and it may give rise to these kind of excitations. Even with modern technology, there are a lot of CCTV, petroleum stations, oil platforms. They have observed, they have recorded the occurrence of these rogue waves in the open sea. Akhmidev, in one of his physics letters A paper, waves that appear from nowhere and disappear without trace. So that's the title of a paper in which towards the end, he speculates that the ships disappearing in the Bermuda Triangle could be possibly because of these rogue waves. So happening it in the nature is nobody has seen it, or nowadays they have recorded it's a random process. So can it happen in a lab? And people have worked out. I will mention it, optical rogue waves, as we go along. So the question interestingly still remains, what are those specific initial conditions that lead directly to the appearance? In general, it is more or less accepted that the modulation instability is considered as a precursor for the soliton formation. So a plane wave which is breaking up in terms of a trains of waves finally could lead to solitary waves. So 2007, the Solly et al. Has claimed an optical counterpart of this hydrodynamical rogue wave. They performed a series of experiments in a specially designed noisy optical system and observed the generation of occasional solitons. They have this property, they appear as a dramatic intensity spike on a low amplified background. In other words, they have observed rogue waves. So the results are also supported by modeling the phenomena after a generalized Schrodinger equation. All these nonlinear evolution equations so far considered have the coefficients, the third order coefficient, the dispersive coefficient, the higher order coefficients. There the coefficients are really constants. Whereas for a real system, these constants may not be real numbers. They could be functions of the different variables, independent variables. In the case of a water wave, it could be variational depth and width. In case of a optical fiber, it could be tapering, it could be the joints. So inhomogeneous differential equations we have to consider. So the nonlinear evolution equations which have been considered so far, we have to generalize that and study now variable coefficient evolution equations that may represent the real system. So what is it we are interested is studying the possible existence of solitary waves for variable coefficient evolution equations. That's going to be the motivation for us in the next few slides. So as I mentioned, one such thing is a tapered graded index fiber. So these can be used as a coupling and branching devices. It's useful for clocking and fiber optic sensor. So what's going to happen here? The refractive index is going to be dependent both on Z and X as well as on the intensity. So how to, okay, it's not only just in optical systems, even in BEC, you have to come up a nonlinear Schrodinger equation with a trapping potential. That's a one-dimensional Gross-Petrovsky equation, describes the dynamics of a Bose-Einstein condensate in the trap. Okay. So formation of matter waves in BEC is well studied. Even with periodic perturbations have been studied by Hasegawa-Kodama, and soliton propagation through density gradients has been studied. So in general, now there is a well enough motivation to study a variable coefficient evolution equation. So here you could see the cubic nonlinearity is tuned with R of t, and this BEC is put it in a harmonic trap as well as a time-dependent harmonic trap. So Sirkin has looked at this problem and he showed that this variable coefficient NLEE is integrable if there is a relation between the trapping, time-dependent trapping and the cubic nonlinearity. So when this condition is satisfied, we have shown that this equation is integrable. In general, the Pomerenko and Agarwal, they have studied the NLSC with the tapering, with a loss or gain. G of Z is dependent on U. So now this is again another inhomogeneous equation, which it was shown that it admits solitary waves, solitons, breathers, rogue waves. So we are interested in these kind of inhomogeneous generalized nonlinear Schrodinger equation, where f of Z and g of Z are functions, and x square is the trap in the context of BEC, x square is the tapering in the context of the optic system. So a gauge and similarity transformation approach has been used by Ponomarenko and Agarwal. So where W is known as the width function, so U has been transformed in terms of e to the power I phi chi. So phi, xi, and W are unknown functions. So they could use a series of these transformations and reduce this inhomogeneous equation down to NLSC. Now all the NLSC solutions are known. So you work out backwards and obtain the solutions for inhomogeneous equation for different f's and g's. If somebody has some other interest, you put a h of u, h of z, or h of z comma x, and again you perform these kind of similarity transformations, and you can end up with any one of the known integrable models. And one can work backwards and try to solve the inhomogeneous equation for certain class of these functions f, g, and h. So while doing this transformation, this is a very lengthy algebra, which I have omitted a lot of details. In that process, what one observes is a relation between f and g and the width of the function. So you remember, w is the width, that is the function which has to be determined, and f and g are the model parameters, model functions. So the reduction to inhomogeneous to NLSC goes through series of transformations where this kind of constraint appears. In the case of Sirkin, this is the relation between the time-dependent trap and the cubic nonlinearity. So here is where we made an interesting observations few years back, almost 1 decade to the day, that d square w by dz square minus f of z w equal to 0, or even this equation, resembles like a Schrodinger equation, d square psi by dx square minus v of x minus e. So energy I have absorbed here. So looks like a Schrodinger equation if I identify f to be the potential minus energy and w to be the wave function. Okay. So with some background of classical field theory or quantum mechanics, that was the time supersymmetric quantum mechanics was being very popularly discussed. So we made this observation that isospectral Hamiltonian approach to supersymmetric quantum mechanics can be invoked here. I will explain what is this approach in the next 10 to 15 minutes, as the result of which variety of tapering profiles can be generated. So we don't have to do the problem all over again for each of these f's. So for a class of f's and g's, we can really give you what is the intensity, and we can control the intensity, amplitude, and width. That is the outcome of this exercise, that a class of f's and g's, we can solve the problem using this isospectral Hamiltonian approach. Okay. With this motivation, this is now completely a digression to the NLLE part of the talk. So if the students are of MSc level, they can really enjoy this part of the talk. How much of data is needed to fix the potential uniquely? This is a very standard problem in 1920 and 1930s. Once the quantum mechanics formulation was done, the question is the simple harmonic oscillator the only one which gives you equal level spacing? Or is the Coulomb potential the only potential which gives you the spectrum minus 1 over n square? How much data? Those are the days experiments are ahead of theory. You got lots and lots of data is coming up. And let us imagine the situation that somebody does a series of experiments and find that the energy levels are equally spaced. So one would automatically think that interaction could be harmonic. Let us suppose he does another set of experiments where the mean displacement is not 0. So for a harmonic interaction, mean displacement would be 0. If it is not 0, what happens? He would try to add an anharmonic term. But the moment you add an anharmonic term, the agreement with the equal level spacing may get spoiled. So you have to make a choice whether energy levels are more important or the mean displacement is important. And you would compromise it one or other and you live with it. So which means how much of data, suppose the another data could be mean square displacement, something else. So how much data is needed to fix the potential uniquely? This is a classic inverse problem. So the answer turned out to be there are infinite number of potentials which will give you equal spectrum. It's not simply to harmonic oscillator, to any problem. So this was beautifully discussed in Jost and Kohn, Infeld and Hull, Abraham Moses, Persa and Lubatsky. The first four references, basically a second order differential equation you solve and you bring out the interesting ladder operator structures, etc. But the supersymmetric quantum mechanics, where a second order operator can be written as product of two first order operators and invoking the supersymmetric structure, Sukumar, Melnick, NATO, Scottney. These in the reset context, these become more easy because you have to only play around with first order differential equations. So life would be that much simple, and really we could get interesting observations by looking at it. This way of looking at the problem. Now, let's go back. There are, as I made a claim, that harmonic oscillator is not the only one which is equally spaced. There are very many number of potentials which are equally spaced spectrum. What is the difference between that and the harmonic oscillator? Energy spectrum is same, but wave functions, normalizations, reflection coefficient, transmission coefficient, once wave functions are different, mean displacement would be non-zero. Lot of interesting features will come. So spectrum would remain the same, but other wave function dependent quantities are completely different. Okay? So this, in a dramatic way, you can see in this view graph. That is the pure harmonic oscillator. There is a parameter called lambda, which I will introduce after a few minutes. So lambda takes one value. This is an harmonic potential. Lambda takes second value. That is the another potential. So I have pictorially represented only for 3 lambdas. You could have it any value of lambda as possible. You can generate infinite number of potentials. All these potentials have exactly the same eigenvalue spectrum. Because these potentials are no more symmetric, wave functions will not be symmetric, mean displacement or any other wave function dependent quantity, if you calculate, that will depend on these parameters, and you can fit as much as you like with your experimental data without destroying the agreement you have already reached with the harmonic oscillator model. I hope some of you might have appreciated the philosophy behind this construction. And harmonic oscillator is not just the only one example. This is a view graph from Reviews in Modern Physics of 1970s. Square well potential. This is the isospectral potential which has the same spectrum. This is the oscillator, deformed oscillator. Particle in a box. So this is the potential which also have exactly the same eigenvalue. Wave function dependent quantity could be different. This is the Coulomb problem. So this is the standard Coulomb problem. So this dotted line also gives you the same spectrum minus 1 over n square modulo small changes. This is a 3D problem, half-line problem. So small subtleties are involved. Otherwise, these two also have the same spectrum. So this is not just unique to the harmonic oscillator. In principle, you can do it for any quantum mechanical potential. So these pictorial descriptions, let me explain how it happens in mathematics. This is an interesting work by C.V. Sukumar. that once you know the ground state wave function, energy can always be absorbed in the potential. Once you know psi 0, the Hamiltonian can always be factorized as A dagger A. This W in the supersymmetric quantum mechanics language is known as superpotential. So the potential is W square minus W prime. Okay, it's very easy to see in the context of harmonic oscillator, W is X. ddx plus W minus ddx plus W, that gives you X square plus 1. So W is X square and W dash is 1. So potential is X square minus 1. So it's very trivial to see for a harmonic oscillator that this W can be constructed, superpotential can be constructed by minus ddx of log psi naught. So only the information of ground state wave function is needed to factorize the Hamiltonian. So let's accept that A dagger A is the factorization. Once you do this, you multiply from the left by A. So A dagger is another Hamiltonian which is having exactly same energy eigenvalues En, and the wave functions of the new Hamiltonian are A times psi. So let us call that as chi. So I have constructed for you, if H1 is the Hamiltonian, En are the energy eigenvalues, H2 is another Hamiltonian with same eigenvalues En. So the potential here is V1, potential here is V2. That V1 is W square minus W prime. Here V2 is W square plus W prime. So the potential profiles will be different. These are called supersymmetric partner potentials. One thing what happens is if A psi is 0, then that will not be there at all. So the spectrum between these two Hamiltonians, they will be one level which is missing. And you can construct the second problem's eigenfunctions from the first problem eigenfunctions. Pictorially, this is what happens. You got a Hamiltonian, H1. You know the ground state wave function, you can factorize it. This is A dagger A. You can construct A dagger. So this state is missing. So there are n levels. This will have n minus 1 level. You start here as your original problem. From n minus 1 level, you can go to n minus 2, etc., etc. This is the standard way of constructing supersymmetric partner potentials. If you have the information about all these wave functions, by using suitable operator, you can construct the wave function for this, wave function for this, wave function. So completely a new potential has been created with the information about the old potential and the wave functions. So that is how new potentials in the literature were worked out by Gendenstein, Sukumar, Khare, Sukhatme, Cooper in that beautiful supersymmetric quantum mechanics book. So this is a standard way of generating partner Hamiltonians. We won't follow that route. We'll ask a slightly different question. We have made the factorization A dagger. We will ask the question, is the factorization unique? Let us suppose there is another factorization B dagger. Obviously, if W1 equal to W, A equal to B, that is a trivial solution. But if not, okay, this is a Riccati differential equation. That Riccati differential equation can be solved. This first order differential equation, this Riccati parameter C is the integration constant here. So what did I do here? I am not happy with A dagger. I constructed B dagger, which is absolutely equal to, identical to each other. So at this stage, I haven't done anything new. But if I ask the question, what is A dagger A or what is B dagger B, that is not same as this. Okay? So that's the crux of this matter, that this is my old problem, original problem. This is the called parent Hamiltonian. Using the standard supersymmetric technique, I constructed a daughter Hamiltonian. This is the ground state of the daughter Hamiltonian. So basically here I have removed one state. Now I am asking the question, can I reintroduce the state? If I reintroduce the state, will I get back here? Answer is no, you will not only get back here, you will get back to any one of those. That integration constant, taking the value of infinity, will give you the old problem. If that is different, you will get different strictly isospectral Hamiltonians. In the supersymmetric quantum mechanics language, there is one level missing. Here, nothing is missing. All these Hamiltonians have exactly the same eigenvalue spectrum, and construction of these eigenfunctions can be done using 3 operators involving V and V1. So, removing a state while reintroduction involves solving a first order differential equation. That integration constant can take any value it likes, modulo few conditions. Taking it to be infinity gives you the original problem. Otherwise, it gives you these problems. Okay. So let me go back to one here. In this particular problem, lambda equal to 10, that is as good as my infinity. So when my Riccati parameter goes to very large value, I will recover the original problem. Any other lambda, I can get a different potentials. All these potentials by construction are strictly isospectral. There is nothing approximation involved here. So this picture is valid, lambda 1, lambda 2. Now, if I remove 2 levels, you can get a 2-parameter family of potentials. In principle, inherently, there are free n number of parameters are inside a n-level problem. So that's a very interesting exercise. So you can construct that family. Lambda is my Riccati parameter. In some places it is written as C. I'm sorry about that. So the potential is the strictly isospectral is V hat, V minus that. The ground state wave function, you can very nicely construct it. And as you notice, if I take lambda to be infinity, I can just take out the lambda, it cancels out, I will get psi 0 hat will become exactly psi 0. Okay, lambda square, take out the lambda and cancel it out. So what are all the admissible values of lambda? All values of lambda, but 0 to minus 1. If this is a normalized wave function, 0 to minus 1 is not allowed, because in the denominator that gives you singularity. Okay, but for this small open interval 0 to minus 1, all other values of lambda are allowed. In that view graph, we have taken lambda to be positive. So all the deformations are on the left side. If you take lambda to be negative, it would be on the right side. And in general, for the whole spectrum psi hat of n plus 1, you can construct not only 1 parameter, you can construct it for 2 parameter also, and ad infinitum. Okay. So that's where we got into this thing, that isospectral Hamiltonians are 2 Hamiltonians which have same spectrum, but wave functions are different. any other wave function dependent quantity other than the Hamiltonian, that would be different, and you can use it to match your experimental results or generalize the models. So this idea we got it, and we have first implemented it in the case of 5-4 field theory. So kinks or lumps are spatially extended finite energy solutions. 5 to the power 2n theories are there. 5-4 theory is the standard one, 5-6, etc. If these solutions have extra property, they are called solitons. Sine-Gordon model is a solitonic model, whereas 5-4 theory is not a soliton. Okay. Now the 5-4 and Sine-Gordon appear to be a drastic restriction. Exactly same shape may is difficult. So people have generalized a parametrically modified Sine-Gordon model. So R is a free parameter here. If R equal to 0, the potential is 1 minus cos phi. That is the Sine-Gordon model. And if R is not equal to 0, this is the work by Perrod and Remosant. They showed that this model has implicit kink solution. So how do one go about constructing these kink solutions out of a model? This is a famous quadrature method. So let's consider a Lagrangian in 1 plus 1 space, 1 time dimension. Mu takes 0 and 1. Let us take the static case. The Euler-Lagrange equations are d square phi by dx square is dv by d phi. So quadratures, multiply by d phi by dx both sides and integrate. You get half d phi by dx square is v of phi. So you integrate this equation. So d phi by square root 2 v of phi is x plus x naught. This is the famous quadrature method of solving it. Take any potential here. You do this integral. Look at Gradstein and Regic book. And the only condition is that v of phi should be at least doubly degenerate. For a 5-4 model, this is phi square minus 1 whole square. So square root of it will be phi square minus 1. So d phi by square root phi square minus 1. That gives you tan hyperbolic inverse. So implicit function, you invert it. So the solution phi is tan hyperbolic x. In the case of a Sine-Gordon model, you get tan inverse e to the power x. So that is the kink solution. So any doubly degenerate potential, you can put it here. If you are lucky, the answer is a simple function. You take an inverse of it. Otherwise, implicit kink solution can always be obtained. Now, how do you study whether these are stable or not? So you do stability analysis. You perturb the field around the kink solution. So perturb the kink phi of xt, kink solution, plus small perturbation psi x comma t e to the power I omega t. When is this said to be linearly stable? If omega square is less than 0, is not allowed. Omega square is always greater than or equal to 0. If that you can show, then the equation is linearly stable. So what does one do? Substitute this in the field equation, then you get a stability equation which resembles like, so this is the 5-4 potential second derivative. You substitute tan hyperbolic x, you get a secant square potential. So this is like a quantum mechanical problem. Schrodinger equation with eigenvalues. This theory has invariance, translation invariance. As a result, 0 mode is there. So the solution starts with omega square is greater than or equal to 0. So it is linearly stable. And that 0 mode is nothing but the derivative of the kink solution. That is again a symmetric property. Now that I know what is the 0 mode of this problem, I can construct an isospectral deformation of this. If I integrate it out, I get the kink solution. So now I have for you, looking at the 0 mode of the stability equation, I have constructed you a new kink solution and hence a new kink model which admits that potential. So this would be the general new potential. This is the Riccati parameter. As you vary this parameter, I have generalized this problem, and basically these are all the potentials. The original potential is 1 minus cos phi. I have generated using isospectral transformations these class of potentials. C can take any value it like, and these are all the various potentials which share the same stability data as that of this. The stability data remains the same. This E0, E1, E2, E3, whatever is the stability data of the 5-4 model, Sine Gordon model, the same stability data will be shared by all these potentials. So these are that is how the parametrically generalized the Ramazan Parad model, where different values of R you have to do it differently. Here I don't have to do that. For any C, all these models share the same stability data. And you can notice the degenerate minima remain exactly pinned to the same place, only the potential may not be symmetric, and the peak, the height of the potential varies as a function of C. That's how we could generalize kink models, not necessarily for 5-4, and you can do it for 5-4 also. These are some of the models, different values of Riccati parameter we could generate. These are all non-polynomial 5-4 models. They share the same stability data. Once we learned this technique, we thought let's try to apply it for a realistic diatomic molecule. So there, the most potential is the model which works. The energy eigenvalues are known. The eigenfunctions are known. So once we need only the information about the ground state wave function, once that is obtained, you can get a deformed most potential. Energy levels remain the same, but in molecular physics and atomic physics, the Frank Condon factors and R centroids, these are the quantities which are observables other than the energy eigenvalues. So if we can now fix the energy eigenvalues to be the same and change the values of these physical quantities, either R centroids or Frank Condon factors. These Frank Condon factors are basically overlap of wave functions. So by now you are familiar with it, what I am driving at. So these are the class of deformed Morse potentials which share the same eigenvalues, but wave functions could be different. You can write down all the wave functions. You can calculate the other physical quantities in terms of the deformed wave functions, and those are some of the values, deformed Frank Condon factors as a function of lambda. That's one interesting application which found its place in literature. This is another interesting problem which we have done it with Avinash Khare. A particle in a uniform magnetic field. This is a well-known problem. This is a two-dimensional oscillator, Landau level problem. So particle in a uniform magnetic field along z direction. Classically, the particle will go in a circle in the xy plane, and it's a two-dimensional oscillator, nx plus ny plus 1 h cross omega. That is the energy eigenvalues. What happens if the particle is in a non-uniform magnetic field? So people can do only adiabatic studies if it is slowly varying, etc., etc. What we found out using this, whether this technique can be used, very straightforward. So this is the Pauli Hamiltonian for a charged particle. So these can be written as A dagger A, is a two-dimensional oscillator. If any interested student is there, if you take f equal to 1, If F equal to 1, magnetic field is constant. Okay, so rho square it will be there. So that's the rho square is x square plus y square. So two-dimensional oscillator. If F is constant, that is a number. This is 0. So it's two-dimensional oscillator. Okay. So two-dimensional oscillator, ground state is infinite fold degenerate, otherwise Landau level problem. Now that can be factorized very nicely like this. And once we know what is the ground state wave function, we can construct what is the deformed F hat and correspondingly what is the deformed magnetic field. Of course, you can't do it for any deformed magnetic field. A deformed magnetic field which is related to the uniform magnetic field. In such cases, you can solve the problem. Okay. So here the Riccati parameter is -20. So that is almost constant. And these are the different values of the Riccati constant. These are all the magnetic field profiles we claim that gives us the same energy eigenvalue spectrum as that of linear problem. Of course, there is a small caveat which I have already mentioned in the context of Coulomb problem, that here M comes. So for the same M, we reproduce the Landau level problem. Okay, I won't go to this detail. We looked into this problem also, that information entropy, rho log rho. So there is the identity which is stronger than the Heisenberg uncertainty principle called Bianchi-Bernoulli-Michalewski inequality. The entropy in the position space and momentum space is bounded, n log 1 plus pi. So for a finite n level problem, we can show that information can be rearranged in a given level. We took a 3-level Scheck square problem and we showed that the information in the position space can be rearranged using this Riccati parameter. So actually these are all the kinds of works which have appeared. This is the Frank-Condon factor effect. Rearranging entropy was appeared here. Kink models here, Khare and isospectral. This is the first work of 5-4 generalization occurred some time back. So we made a long digression for more than 20 minutes. So let's get back to our work. Okay. So currently, if you remember, this is where we ended up. D square psi by dx square minus v of z psi is 0. So for a class of F and G, Sherkin and all, Pomerenko and Agarwal have solved the problem. We identified that for a different class of tapering functions, you can really solve this problem. And W, if you remember, width will occur in the denominator of the solutions. So that will be dependent on the C. By choosing the value of C, you can increase the intensity or the width of the function. This is the observation, that's it, nothing more than that, with the prior knowledge that what is happening earlier case. Okay. So let me now, this is one of the typical examples of Sherkin work, that there is a width function, there is the nonlinearity, and this is the gain or loss function. So these are the profiles for which one can work out what is the amplitude of a solitary wave. Now, the presence of C makes these small variations in F, these variations in W, these variations in the gain function. You can, with these small variations, see in the dispersive management, etc., if you have any other F's, you have to do the problem all over again. Here what we are saying is, for these class of variations, our intensities are here. C equal to 10. That is as far as infinity is concerned, that is the original problem, and C is 1 and 0.1 are the next panels. This is C is 1, this is C is 0.1. All families, be it a bright similariton, Akhmedev breather, first order rogue wave, second order rogue wave. You can see the amplitude. Here it is 3, 10, 60. Second order rogue wave, 30, 40, 150. First order rogue wave, 10, 15, 60. Breather. So basically what happens is the width function is now dependent on the parameter. Once you choose a proper parameter, you can really make a intensity as high as you like. Okay. So this is one of those PRA work. So once it's not only the rogue wave of the first order, in a water tank experiment, Chapchov and Akhmedev, they observed rogue wave triplets in water waves. This was in 2013. Okay. So there they make two interesting observations. The major difficulty of the experiment with second order solution is that it requires long propagation distances. These are longer than the actual length of the tank, which is a limitation. To overcome this difficulty, experiment can be done in sequences. So instead of water wave, they make a suggestion that this work may also motivate similar experiments in optics. Advantage of fiber optical setup is arbitrarily large propagation distances. That can be realized avoiding the restrictions that we have in case of a short water tank. So a triplet water wave, the triplets have been generated. Now for a different class of F and Gs, what we could do was the distance between these triplets and the amplitude of these triplets can be modified if we do the Riccati way of doing it. So this is the work without a Riccati parameter, which we reported. And then once you do this, you can really rearrange or organize it. The length can be made small or the time span can be reduced. You can, observations could become very easy by choosing the proper Riccati coefficient. So that was the work consequent to the Akhmedev's work. We people worked on it, and this appeared in 3 letters A. The similar analysis could be done in the context of BEC. So BEC, as I mentioned before, so this is the cubic nonlinearity, this is the trap, which Sutkin has made it time-dependent cubic nonlinearity and time-dependent trap. And the integrability condition is between R and omega. And what we could do was isospectral deformation. This worked in a IEEE journal, that you can really, intensity profiles can be managed using the Riccati parameter. And it's happy to note, you feel really happy if someone recognizes and put it on a journal's cover page. This is EPJ special topics. This work is done in collaboration with Prashanta Panigrahi and T.S. Raju and some of my students. So that work, BEC rogue wave, the cover page for a EPG special topics issue. So as I mentioned, most of this work is done in these groups. Okay, so let me, that's the part of how to control the intensity using the Riccati, and along with it, the Riccati, how it was useful in other contexts of physical situations. So I have to really express my thanks to my teachers. Avinash Khare, he was my supervisor. Professor R. Rajaraman, I got a chance to interact with him at CTS, Center for Theoretical Studies, IISc Bangalore. He was a good inspiration, and in quantum field, classical field theory, his book on solitons and instantons was very well known to many people. As a physics reports, before the book came out, the physics reports used to be our Bible. And let me express my thanks and gratitude and reverence to Professor Lakshmanan. Though we directly did not interact with him many times, he and his group has given us lots of opportunities, be it at Pondicherry University, be it at BDU, a lot of people, Parshajian, Daniel, Tamajmani, Professor Lakshman, the school, he arranged so many programs. Especially I remember the Indo-French schools like Vadati, Krushkal. So interaction with those people, Balakrishnan, etc., etc. So I consider him like my spiritual guru, or basically nonlinear physics. I learned quite a lot from his work and from his book, though not directly from him. So let me express my thanks to these three people. And Prashanta and Solomon are my collaborators for quite some time. And Viswajyoti, Durga Nandini, and few others were for one or two works in this context. A lot of this work was done with my students at different stages. Amit, Rama, Shalli, Harleen, Kanchan, Vivek, Vitupal. And presently we have students working in, some of them in PT symmetry, some of them in supersymmetric quantum mechanics, and there is an interesting W function. So we are all working in this area, and I'm really enjoying working with my collaborators and with the blessings of the teachers. Okay. Thank you all for your kind attention. So I stop my presentation here.
Thank you, Kumar. Thank you for a very interesting talk. Now it's time for questions.
Hello, sir. Am I
Yes.
audible, sir?
Yes, Prasad, you can start. Yeah.
Yes. Sir. Actually, I have some questions from the basic of the soliton theory, sir.
Yeah.
So, actually, sir, I was confused between like we have mod log fiber ledger. So there, with the help of mod locking, we are. Am I audible, sir, to you?
Yes.
Yes, sir. So with the help of mod locking, also there will be a generation of soliton. But those soliton, I think they'll be different from the deformation in the electromagnetic field, right?
Okay.
So will there be some kind of
See, what is it that we have done here? If you could solve it with a inhomogeneous equation with certain kinds of nonlinearities, if the nonlinearity profiles are slightly different, you have to solve the problem all over again. Instead of that, if the deformities are of our kind, then you don't have to do any extra work. You can just straight away see, for a class of F and G, if you can solve the problem, we can generalize the dispersion management by suitably tuning the Riccati parameter. Okay, so I am not really into any experimental thing. I am just looking at it as a mathematical equation. If you want, okay, let me just see whether, okay, yeah. Let us suppose equation 70, is it visible?
Yes.
Okay, so now somebody has done it for a particular R and particular omega. Okay, now what is it I am going to tell you is, okay, where is that graph? Yes, yeah, one more minute, one more. Yeah, this is the F and G's. Okay, for these class of deformities, I don't have to start the equation ab initio, and I am giving you the prescription of how to get the intensity increase. You tune your nonlinearity like this, your intensity will increase. That is the take-home point here. Let me give you another example. See, if you have a uniform magnetic field, you will get equal level spectrum. Is that right?
Yes.
If you have a non-uniform magnetic field, you don't know what is the spectrum. But if the non-uniformity is of my type, if the non-uniformity, you can get it by tuning the Riccati parameter. That will give you the equal spectrum. Okay. So the dispersion management for different kinds of functions you do the problem. What I'm trying to tell you is in the same function, there is a parameter. I can play around with that parameter to change the profile of the system. Okay, Prashanta ji, if you are not following, maybe you can send an email. We can talk over it separately. Okay?
Okay, sir. Okay, sure, sure.
Prasad,
Yes, sir. Yes, sir.
Okay, I think he is gone.
yeah.
Sir, I'm audible, sir?
No, we are not able to hear you.
Okay, sir.
Who is speaking?
Sir, Prashant, sir. Prashant, I'm speaking.
Prasad, no.
Yeah,
Prasad,
I lost the
we are
connection.
not hearing you.
Okay. Hello, sir. Am I
Yeah,
audible
yes,
now?
yes,
Ah.
yes.
Okay, okay, sir. Yes, sir. Actually, I was able to get, sir. Actually, like in mathematical sense, you asked, sir. So in mathematical sense, I think it is like the dispersion management and dissipation management.
Yes.
Like dissipation versus nonlinearity and dispersion versus nonlinearity.
Yes.
So I think in mod log case we have dispersion versus nonlinearity, and if it is like continuous field, and there we have a kind of deformation. So there we have to consider like the dissipation term in the like that equation, and some nonlinearity term. So I was just thinking that some kind of characteristic difference between these two kind of solitons. So
No, okay. What is it we are doing is we are generalizing all those dispersive management functions that f of z and g of z. We are generalizing it, and the effect of the parameter on the intensities or the amplitudes or the width. It's a simple observation. There's nothing fundamental about it, but utilizing that, we can enlarge the class. That's the observation we have made.
okay, sir. Okay, okay. Thank you, sir.
Yeah, Nagaraj Kumar, it was a very beautiful lecture. I really enjoyed it. Are you able to hear me? Nagaraj, are you hearing me?
Yes.
Yeah. I have a couple of remarks or points to make. One thing is that in BEC, I think several years ago with my student Rajendran and Muruganandam, we have considered the several forms of R of T and Q of T with the Riccati connections.
Okay.
And we have pointed out how all these for general forms one can map onto the nonlinear Schrodinger equations, and interesting class of waves can be obtained.
Yes.
So I think your results remind me that these results can be further modified by incorporating variation in Z also.
Absolutely, absolutely.
That's very nice.
Actually, let me interrupt. Actually, I had a discussion with Muruganandan before about this.
Oh,
I think he had some work with Sadhana Adhikari or someone, BEC.
Yeah.
So in that context, he is aware of it. We are doing it like this, but we never really got together and mapped out anything.
Yeah.
But I remember his work that coupled two field BEC, I think.
Yeah.
Yeah, I am aware of that work. Yes.
Manakov equations.
Yeah, Manakov equations. Yes.
Yeah. Then the other thing is there are a number of recently a number of position dependent mass systems along with my collaborator Chitiga and also Sendil Velan. We have identified, I mean, we call them nonlinear Leonard type oscillator classically.
Absolutely.
But quantum mechanically, they lead to position dependent mass.
Yes.
And several examples lead to just harmonic oscillator spectrum.
Yes.
That in the they are all PT symmetric. They lead to PT symmetric potentials.
Yes.
In the symmetry preserving regime, the spectrum is exactly same as that of the harmonic oscillator.
Yes.
But we solve these potentials in momentum space,
Yes.
not in the coordinate space. Though, so the eigenfunctions take in momentum space. They have you can express in terms of kind of Hermite type polynomial and exponentials. But when you go to position space, you have to take Fourier transforms and so on.
Yes.
So, and very recently with Chitiga, we have identified a class of other position-dependent potentials which lead to the same kind of harmonic oscillator-like spectrum. They have appeared recently in Journal of Physics A or Journal of Physics A Communications or something like that. So very recently in 2022 or 21 late. So I just wanted to.
I'm completely aware of this work. Actually, if I remember, Senthilvenan remembers when he gave the talk, he gave the references, we downloaded it, ML oscillator, position dependent mass. If you know psi 0, even that EPJ I am referring to had your article, articles that Ambika edited volume special topics. Yeah, it has ML oscillator and position dependent mass.
Yeah. So there has been a lot of further developments.
Absolutely, yeah. The only point is, I was asking my students also, that's a beautiful piece of work, position-dependent masses. Even that Bijan Bakshi also used to do kind of work. And if I remember Senthilvelan, we did discuss about it and you gave me the references. We downloaded ML's paper. Yeah, we are aware of it and one can really look at it. How, if you generalize that model, if a Riccati parameter can enter into that, how does the position dependent function, the mass dependent function, how does it vary? Can you make it realistic to a like harmonic oscillator? Yeah, that's very good. We are aware of the work. Somehow I did not go into the ML of the quantum mechanical oscillator part of it in this talk.
Okay, nice.
That's the reason why I never expressed it in so many words, but in the back of the mind, you are always stalwart in nonlinear area.
Yeah.
It's not,
So it's a pleasure to enjoy your talk. Yeah, to listen to your talk. Thank you.
Thank you.
So, questions from others? Okay, so I'm not getting.
Hello, sir.
Prashant, you want to talk? You want to raise some questions?
Yes, sir. One more thing I had, there is a stability analysis of that soliton.
Yes.
So in that stability analysis, we are giving some kind of perturbation, and we are getting that. So is there any kind of relation between limit cycle and the shape of the soliton, the solitary?
No, these are all, no, there is no relation between the limit cycle and this. See, once the 5-4 field theory, once the field theory has a certain invariance, the stability equation always admits a zero mode, and the stability equation zero mode is derivative of the kink. So that's the straightforward Rajaraman way of doing stability analysis of a kink. So there is no limit cycle does not enter into this analysis.
Okay, so one another, so because I want to know, have you found any kind of the interaction between two soliton could be periodic energy sharing kind of something? We could see there could be a sharing between two solitons, but periodically they are getting change. Once is it is E1, then E2, and again E1. That it is just oscillating between two solitons. Is there something like that?
I am not aware of it. That is the work I mentioned about that 64 enharmonic oscillator Fermi Pasta Ulam problem. Okay, so 64 oscillators, you give energy to different modes. You expect the equipartition theorem and all the modes will get equally excited. But lo and behold, that don't happen. The energy comes back to the original mode after a big long time, and you take a continuum version of that enharmonic oscillator that turn out to be the KDV equation. Is that right, Shantil?
Yeah. Yeah, it is.
That's the analysis.
Yeah, it is available. The matter is available in the professor's book.
Okay, sir. Okay.
Okay.
Thank you so much, sir.
So, any other questions? No, if not, let me conclude the session by thanking Dr. Nagaraj Kumar for giving a very interesting talk on solvability of a variable coefficient nonlinear Schrodinger equation. Thank you, Kumar, for accepting our invitation and giving a lecture here. I will write to you other matters by email.
Okay, sure.
Yeah.
Welcome.
Actually, personally, I was expecting you will be giving some more. You will talk about your recent papers.
Oh, well, this is something I thought interesting for, actually, the earlier days I have seen a lot of MSc students sitting in the big lab and all. So part of these works I have given it as a MSc project student from my 4th semester students.
Yeah, actually, unfortunately,
So that's why.
we MSc students are not present.
Yeah, maybe some other time we can meet and discuss. Actually, that MLSUS problem was an interesting one. We should look at position dependent mass, that problem actually.
Okay.
Yeah.
Thank you, Kumar. Thank you.
Thank you. So nice. Thank you for giving me opportunity.
Yeah.
Thank you.
Thank you.
Should I quit?
Yeah. You can leave that.
Thank you to everybody for patiently listening.
Yeah, sure.